You know, it's fascinating how fire, this thing we kind of take for granted, right? It's been like this cornerstone of civilization, but also this looming threat throughout history. It's almost like this weird love-hate relationship, but with a chemical reaction. And speaking of chemical reactions today, we are diving deep into the world of combustion chemistry and carbon neutrality.
In this paper, it's not just some dry textbook stuff.
Mm.
It really shows how intertwined combustion is with like the whole story of human progress.
You know, when I was reading it, I was struck by how our ancestors, they were already manipulating combustion in some pretty sophisticated ways. Like they didn't have fancy labs or anything, but they were still pulling off incredible feats.
Yeah. Oh, totally. They were the original combustion chemists, right? Just figuring it out as they went. And what's cool is that now we can use all these modern scientific techniques to like retrace their steps. It's like archaeology meets chemistry. We're using tools like FTIR analysis, which basically shines infrared light on pottery fragments to figure out the exact temperatures and fuels they were using in those ancient kilns.
So we can look at the chemical fingerprints left behind and understand how they were controlling the fire to get those results.
Exactly. And the amazing thing is, these aren't just fun facts about the past. Knowing how they dealt with fuel resources and byproducts even back then gives us a whole new perspective on how to approach those same challenges today.
It's like each piece of pottery is a little time capsule with clues about their craftsmanship and the environment they lived in. Talk about a blast from the past.
And speaking of blasts from the past, let's talk about color, like those vibrant colors in stained glass. The paper explains how they got those stunning hues using tiny metal nanoparticles, like gold or copper dispersed in the glass.
Wait, nanoparticles? Like the stuff we use in cutting-edge tech today?
Yep, the very same. But centuries ago, they were creating these nanomaterials inside the glass through this careful dance of heat and chemistry. It's mind-boggling. And now with tools like X-ray fluorescence or XRF, we can actually map out where those nanoparticles are in the glass, revealing the secrets of their techniques.
It's incredible how precise we can be now. Like we're looking right through time. It really makes you appreciate the ingenuity of those early artisans even more. They were pushing the boundaries of chemistry without even realizing it.
Absolutely. And these historical examples, they show us something really important. Combustion isn't just about raw power. It's this delicate dance of chemistry that we've been refining for millennia. And understanding this dance, that's the key to unlocking a cleaner and more sustainable future.
It's amazing how these intricate processes have been happening for centuries, just like right under our noses.
It really is.
Yeah.
But, like any powerful force fire has its downsides. We've gotten pretty good at bending it to our will.
Yeah.
But that control hasn't always been there.
Yeah, you could say things can get a little too lit sometimes. Speaking of getting things a little too lit in the kitchen, I imagine controlling these combustion reactions gets tricky. So is that where the pollution problem comes in?
You got it. Right at its core, combustion is this rapid reaction between a fuel and an oxidizer, usually oxygen, and that releases energy. Think of it like a controlled explosion, a balancing act.
With byproducts.
Exactly. And some of those byproducts, they're not exactly environmentally friendly.
So I'm guessing some of those byproducts aren't exactly what we call eco-friendly.
Right. The paper talks about this thing called the equivalence ratio,
Right.
which basically tells you how balanced the mix of fuel and oxygen is. Like imagine you're baking a cake, right? You've got the perfect recipe, the perfect ratio of ingredients. It's like ideal combustion, what we call stoichiometric conditions.
But if you use too much flour, the whole cake is ruined.
Exactly. Too much fuel, and you get things like unburned hydrocarbons and carbon monoxide. Too much oxygen, and you get an excess of nitrogen oxides. Those are the things that cause smog and acid rain.
So it's all about finding that sweet spot, that perfect balance.
You got it. And the challenge is that achieving that balance, it's not always easy. Especially as we've scaled up our use of combustion for everything. Cars, power plants, you name it.
It's kind of a sobering thought that our reliance on combustion has come at a cost, like we talked about earlier with those medieval cities and their coal smoke, or even more recently, the London smog of 1952.
Yeah, that was a real wake-up call.
It really showed the world how dangerous air pollution could be.
Absolutely. It was a stark reminder that uncontrolled emissions have real consequences. And it really underscores the need for finding cleaner, more sustainable ways to use combustion. This paper makes a strong case that a carbon-neutral future is possible, but it requires a fundamental shift in how we approach fuels.
So are we talking of going all in on electric cars, solar panels, wind power, that kind of thing?
Those are definitely part of the solution for sure. But this paper, it goes beyond the usual suspects. It really dives into some really fascinating alternative fuels, like hydrogen, methane, ammonia, and something called oxymethylene ethers, or OMEs.
OMEs, that's a new one. What makes them so special?
The really cool thing about OMEs is that they're synthetic fuels, meaning you can produce them from renewable sources, like biomass or even captured CO2, and they have some great characteristics. Really low emissions of nitrogen oxides and soot. They're even being explored as a potential replacement for diesel fuel.
So they're clean, renewable, and could power those big rigs we see on the highway. That sounds pretty promising.
It does, but
I was about to say there's got to be a but coming.
You're right to be cautious. The paper makes it clear that just switching to a new fuel isn't some kind of magic bullet. It's about the whole life cycle of that fuel, its production, transportation, the infrastructure needed to support it. That's where things get really complicated.
Because it's all connected. Even if you have a perfectly clean burning fuel, if its production or transportation creates a huge carbon footprint, then you're not really solving the problem.
Exactly. A successful transition to carbon neutrality requires a holistic approach. One that considers not just the fuel itself, but its entire journey from production to consumption. And that takes collaboration. Chemists, engineers, economists, policymakers, everyone needs to be at the table.
It really highlights how complex this issue is. It's not just about finding a single magic fuel. It's a whole system change.
Precisely. And it's about understanding the details of combustion itself. See, up until now, we've mainly focused on what we call homogeneous reactions. Basically what happens when you burn a gas or a liquid fuel. But there's this whole other world of heterogeneous reactions, which involve interactions between gases and solids.
Okay, now we're getting into some next-level chemistry here. Heterogeneous reactions, you say. Tell me more. Okay, now we're getting into some next-level chemistry here. Heterogeneous reactions, you say. Tell me more.
So imagine you're starting a campfire, right? You got your wood, which is a solid fuel. And to get those flames really going, you need those reactions happening between the gases and the solid wood itself.
So it's not just about the flames themselves. There's a whole other level of chemistry going on at the surface of the fuel.
Exactly. And it's not just campfires either. These heterogeneous reactions, they're crucial in things like catalytic converters in your car. They use a solid catalyst to clean up those exhaust fumes. Even fire retardants, those things that help protect homes from wildfires, they rely on these gas-solid interactions too.
Wow. They're everywhere. But how do scientists even begin to study something that complex? It's like trying to watch a microscopic dance.
It is complex, but researchers have some pretty amazing tools these days. One example the paper talks about is the synthesis of iron oxide nanoparticles in flames. They're using techniques like laser-induced fluorescence, or LIF, which is basically like shining a spotlight on specific molecules within the flame that can track their every move.
Iron oxide nanoparticles. So we're talking about building incredibly tiny materials atom by atom inside a flame. That sounds like something straight out of Star Trek.
It does sound pretty futuristic, right? But it's happening right now. And the applications are huge, from pigments and catalysts to next-generation electronics. It's all about manipulating combustion with this incredible level of precision.
It's amazing how far we've come. We talked about those ancient artisans using fire to create art, and now scientists are using it to synthesize entirely new materials. It really shows you the power and potential of combustion.
It does. And this deep dive into combustion, from its ancient roots to its role in a sustainable future, it really highlights how important it is to understand the chemistry happening. It's not just about controlling fire, but about choreographing it, making it cleaner, more efficient, and ultimately more in tune with our planet.
Combustion in all its forms, it's going to keep shaping our world. And thanks to this deep dive, we can all appreciate that intricate dance of molecules a little bit more, whether we're striking a match, starting our car, or even lighting a candle.
It's a dance that's been going on for millennia, and one that will continue to evolve as we work towards a more sustainable future.
It really makes you think. So next time you encounter combustion in your daily life, take a moment to appreciate that unseen world of chemistry making it all possible. It's a world full of challenges, but also incredible opportunities. And understanding that world, well, that's the first step towards a brighter future. Until next time, keep those brain cells firing.